All right, so welcome to Statistical Mechanics, the quantum mechanical foundations of thermodynamics. That's what this class is about. We will start with a review of classical thermodynamics and build step by step. As I alluded to before I started recording, this class, the book, Pathria, should you decide to get it, is really a 2 years worth of material type text, and I have 1 semester. So what my philosophy, the thing that guides me is that I want to be able to do enough that if you want to read something out of that book we don't cover, you should be able to do it with a little bit of work, but it shouldn't be completely opaque, completely to where I don't know what this is. You should be able to get to that position. All right, so let's start with I've talked to you already about what you've had. So you've been here and you've taken quantum, you've taken what was your degree in back home?
Bachelor.
Okay. Okay. You had here what mechanics book did you use? Goldstein or Taylor?
Maybe. Uh,
I know quantum you use Shankar, right?
Shankar, yeah.
Yeah.
Oh,
E&M you use Jackson, right?
yeah.
What mechanics book did you use? You remember?
Classical mechanics.
Yeah.
It's Dustin.
Goldstein. So this is your second year. So you're doing right now math methods. You're doing this class, advanced lab,
Advanced lab.
advanced lab. Who's doing advanced lab? Kennedy?
Neil.
O'Neill?
Yeah.
Okay. All right. All right. So this class will doesn't you asked me this question, so I want to address it in case you have it. You don't need a lot of statistics. When you see the word statistical in this class, it's really not about, the Z or the T function and Gaussians and all that. That's not what it means. It means averaging. That's what the statistical in my mind means in this class. It's averaging. So really, the average value of a function is the integral of the function dx between a and b, the average value in that integral. It's really just a sum, right? That's all you really need. Averages and a couple of standard root mean square deviations and things like that. So if you haven't had a class, this is a question I asked when I was 21 years old. I walked into there. We had a book, Thermal Physics by Cattell. I said, I have never taken a course in, I don't know what variance and mean and all mode, and I don't know what any of those things are. He said, you don't need it. That's not this. When you see the word statistics here, statistical, it really is not referring to those, the things the actuarial people that make insurance tables. Well, you're 34, you have a 50% chance of dying from this. That's not how we do it. This is really statistical in the sense of we take microscopic components, do averaging, and say, look, at this point, uh, we know there's a bunch of molecules in here, and they're all going different speeds. They're all traveling 500 meters per second, 200 meters per second, 1200 meters per second. And yet, if I put a thermometer here, I read 71 degrees. If I put a thermometer here, I read 71 degrees. The idea behind that is you're doing the averaging over all these molecules in that little spot. And we're seeing how they hit the thermometer here, 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 here. And yet it's a remarkably consistent thing. Nature does that averaging for us. And that's what that statistical means. All right. Okay. So the first thing I would ask you is if this is at the beginning too easy. And you say to yourself, oh, come on, let's get to I don't know what everyone knows walking in here. So I always spent a little time going back and to be completely frank, very rare is the student that doesn't benefit from a first principles treatment of these simple things. It's very rare that I don't see a student that doesn't benefit. All right. So you'll see me in the first part of the notes. It says experience. I'll quote myself. Experience has taught me not to assume students enter this course with a strong foundation of the concepts and backgrounds needed to make better sense of the material comprising this subject. And that is why we are going to spend a good amount of time, this set of notes and the next set, which will be particle in a box. He said, I already know how to do particle in a box. I don't care. We're going to do particle in a box, and I'm going to emphasize the ideas that you need in thermodynamics from particle in a box. Because one of the disconnects we have when we teach quantum mechanics is we don't tell you the reason you do particle in a box is to describe the air molecules in this room. Because if I have in my hand an oxygen, see this oxygen in my hand right now? See these walls? It's particle in a box. We don't tell you that, but that's exactly what you need to be able to do a lot of this stuff. And one of the things I'll tell you, foreshadow later, you sit down, you write the Schrodinger equation, and you get the spectra. And if you don't know it, if you don't remember it, the energies are h bar squared over 2ml squared pi squared and nx squared plus ny squared plus nz squared particle in a box. So here you have something, particle in a box, and this is quantum mechanics. And then you have something over here that is heat and work called the Boltzmann factor. It's all thermodynamics. And then you take quantum and you do this and you get out. To me, it's one of my favorite parts of this class. You take the particle in a box, you take Boltzmann's factor, and you get PV as nRT. You get the ideal gas. It's one of my favorite parts of this class. Did you guys do that?
Yeah, something like that.
You something like that? Okay, it's still one of my so it's one of my favorite classes. Okay. So we start with thermodynamic variables and state functions. If you can't read my writing, you just got to let me know. I'll do my better. I'll do my best. Variables. Is that big enough? Or a little bit bigger?
Okay.
It's okay? State functions. And I'll put an underline. Okay. So I'm going to write something down. I'm going to write an arbitrary function down to three variables, and I'm going to call UVW because I don't like the way XYZ looks at the moment. So here's a function. And if I define the differential of a function, it means taking D. And the first thing I would say is to you, you should know what that means. What this means is you increment every variable, U plus du. I'm going to use delta over here like this. V plus dV and W plus delta W. And for it to be a change, actually, you know what? You guys are more seasoned than the average student. So I'm going to go ahead and use the D's here. And you guys understand this is in the spirit of calculus and not finite differentials. So we'll actually write D's here. U V W plus dW. And I have to eliminate the original function. I have to get the change. Of course, we know the D operator. If you don't know this, is du partial partial u plus dv partial partial v plus dw partial partial w. In a calculus class, you then apply here this formulation, and you'll write du. You operate on here. This is partial f. You can also do Taylor expansion. So you can do it that way, or you can, let's do it with it because I don't quite do it this way in the notes. Let's do it this way. Let's take this and Taylor expand it. We know this is then df is equal to f of u v w plus, and then this operator would give me du partial f partial u plus dv partial f partial v plus dw partial f partial w. And of course, what do we have to do? We have to subtract f. And of course, this is what you already know. But I have something to say about it. And that tells me df is, in fact, if you look at this guy, what you looking for? Me?
Yeah.
What you need?
Yesterday, but I think I was coming back.
Yeah, you're supposed to be here at 10:30.
Yeah, I have to speak to my advisor.
Okay, I'll be here tomorrow. I'll be here tomorrow around 11 if you want to stop by.
Class at 11:15.
I'll be here from 11 to noon. I have an office hour from 11 to noon. Everything okay?
Yeah.
All right. I'll see you tomorrow. So df is then, if you think of it in terms of vector analysis, for example, again, it's just a thing I want to add. If you think in terms of if these are x, y, and z, this would be this. Because this would be, if you want to use x hat, because I'm switching variables only because most students who walk in here have not seen this arbitrary formulation. The point I would like to make, and you see me talk about it in the notes, this is a mathematical statement. for what we just did, this is then du partial f partial u, and so on. This is a very important idea. And let me tell you why. You're a physicist, or in your case, chemical engineer. You're not a mathematician. So this is a mathematical statement. df is this. That has nothing to do. That has nothing to do with anything in physics at the moment. That is a statement discovered hundreds of years ago, and it's completely general. Here is the connection we have to start to make. This is a mathematical statement, but what physicists had to do in the early part of the mid to late part of the 19th century. So I would say somewhere around the 1870s, 1880s to the early part of the 20th century, 1910s, 1920s, physicists had to make a connection. This is a mathematical statement, but what does a physicist do? A physicist doesn't have u, v, w as some arbitrary function. He doesn't have this. You're trying to describe physical phenomena. Physical phenomena in this case, in this class, are thermodynamic phenomena. What do we have? We have temperature, we have pressure, we have volume, we have these things I can go in a class and measure. The goal of thermodynamics, in fact, if seen from the broader perspective, the goal of thermodynamics is, in fact, to use these mathematical sets, all of physics, not just thermodynamics, but this happens to be the one we're going to employ today, is to use these mathematical tools to say something about nature, to say something about physical systems. All right. So what they first did is they knew all this, and then they were fumbling around in the lab with all kinds of things. It's a fascinating, the history of thermodynamics is fascinating. So as I said, they have these energy and temperature and pressure and volume and vapor pressure and moles. They had a pretty good sense of all that, but they had to start connecting things. So the first thing they said, so this translation from here to something physical was really something that occurred in fits and starts. I don't know if you guys are familiar with that phrase, fits and starts. You know, fits and starts means you make a little bit of progress, then you stop, then you go backwards, and it's like in your car. You hit the accelerator, you hit the brake, you hit the brake, put it in reverse, you go back. That's fits and starts, and that's what thermodynamics was like. And the key insight was to find a function that they could use to measure the disorder of the system. And this is how they got to where the entropy, okay? So the first step in making progress, first real step after all these experiments and all these Charles law, Boyle's law, ideal gas law, was to start to think of this subject from more mathematical terms. And the way it starts is what's called a state function. And they define this is the first thermodynamic idea we introduced, the entropy. Okay. So the entropy he calls S, and it was a function of U, V, and N. So this is a function of the internal energy of the system. I'm going to label those things. U is the internal energy. You got to start somewhere. V is the volume. And N is the particle number. It took Boltzmann, Gibbs, and other geniuses to demonstrate the entropy of an ideal gas had connections to what we now know as the modern interpretation as the number of ways the system can be arranged. You always hear lay people talk about the entropy as the disorder. They say, they talk, well, that's the disorder of a system. That's not what the pros say. That's not what the professionals say. The entropy has a very specific quantitative. This is what people who don't understand physics say. Disorder of a system. And it's fine. You can say it. I don't have an issue. That's fine. If you're trying to explain, so I have a 10-year-old sitting right here, and he's interested in science, right? And he asks me, what's entropy? Well, entropy measures the disorder of the system. And he's happy because he's 10. But you shouldn't be happy because that's not a quantitative thing. We can't make any predictions with it's a disorder of a system. That's not good enough. As we'll learn later, it's a measure of the number of states accessible to the system, or number of the ways a system can arrange itself consistent with constraints of energy and every other thing that's in the system. Okay. So you'll see I say actually as a historical note, the classical interpretation of S was I could not have done it. I could not have figured this out. That's why it took Gibbs and Boltzmann and these brilliant, brilliant people to figure it out. Okay. So what do we anticipate? Let's say we do say this is a disorder, and I'll put that in quotes because they didn't have a very strong sense at the outset disorder of the system. We anticipate the entropy, and I'll write that out. S monotonically is too small. It's a very important idea. We need a big S. It should increase monotonically. Monotonically, if you haven't heard that word before, means it should never wiggle. That's monotonic. That's monotonic. That's monotonic. It doesn't go up, or rather, it doesn't go down, doesn't wiggle. It's always steadily increasing. The idea was S increases monotonically. Oh, I did it. In U, in V, and in N. So what does it mean to increase? Does this make sense? It does. Think in terms of think in terms again, the disorder of the system. If you put, and for lack of a better system, we'll use an ideal gas. If I have a gas and a piston and I heat it up, the particles in there will go faster. A gas and a piston, I heat it up with a Bunsen burner. Do they call them Bunsen burners?
Yeah.
They call them Bunsen burners back where you get, okay. So they heat them up, you get the gas. That means there is more disorder because you are going faster. Very little disorder would be for the particles not to be moving at all. Heat them up, they go faster. So if you look at one of them, it can be, if you have very low entropy, if it's here nice and cold, doesn't go far, you can count them all. But as soon as you heat them up, they can start to explore their energies, their kinetic energies. If you make something bigger, you think of disorder of the system, it can now be in more places. Think in terms of if you have everything packed in your room, in a corner, in a bookcase, that's nice and ordered. But if you start throwing books all around, you've increased the volume of the books to occupy, and now that room looks messier than what it did before. And in terms of the particle number, if you have zero or just one particle in there, it's pretty obvious what's going on. There's a particle right there. As soon as you put more particles in, they can start to interact. They can start to then explore again the volume. They can exchange energy, and there's a lot more disorder when you have n particles. So it makes sense. And that was really good. Why is that important? Because if S is monotonically increasing, this is really where thermodynamics in the late 1800s started. If it's increasing monotonically, then you can invert it. You can't, do you guys remember? I don't know if they teach this in high school still. If you have a function f of x, and you want to take the inverse f minus 1 of x to get x, or just do it. You can't have this, right? Because you're really taking a slice this way. To invert a function, if it's monotonic, if there's f of x, you're really trying to get it over here. You're trying to project it onto, it's the way I learned it anyway. Of course, this was 100 years ago. Obviously, if you have something that goes up and down, you have different points. This is, by the way, essentially the same thing. Maybe it'd be more familiar to you. When you do inverse tan, it looks like that, right? The inverse cosine on your calculator can only restrict itself between a certain thing, right? You're only really looking at one branch. So monotonic means you can invert it. And this is exactly the insight that they had. I think it was Gibbs who had it. He said, look, because it's monotonic, if I take S, U, V, and N, and instead I do this way, and I'm going to tell you why they did it this way. S, V, and N. The reason they were lucky, the reason we live in a universe, we're very lucky. to live in a universe that's understandable.
Mhm.
The reason, not everything is luck though. There's like some, this is pretty sweet. The reason though they were lucky that thermodynamics shook out this way was because you look at the writings of these guys and they talk about this later. They said, we realized this is a very important idea historically. It was brilliant to introduce that. The problem is you have to think about what you are what you have experimentally accessible to you. The entropy you can't get. You can't go to Ace Hardware. You know what Ace Hardware is? It's a hardware store. You can't go to Lowe's. You know where Lowe's is? No, you don't know. How long you been here? You don't know where Lowe's?
I know Ross, but I don't know.
No, Ross. But you can't go to Ross, okay, and pick up an entropy meter. They don't make them. You can't go find something to measure the entropy. There's no thermometer for entropy, right? You can get a barometer, which measures pressure. You can count the number of particles by adding them one at a time in principle. Obviously, you can't for 10 to the power 22 of them, but you can add them one at a time. And you can add, you know what the energy you add is because you all took, here's a good approximation for the energy. The heat you added, which is the energy in some for a constant volume process, is MC delta T. Do you remember that from high school? So you have control over this, this, and this, but you don't have control over the entropy. So you want to kind of bury it into something you can work with. You want your state function to be something that kind of hides the problem of the entropy. So let's continue. So let's take a differential of U. So we'll do that now. So the total differential of U will be ds partial U partial S. Again, this is in some sense only a mathematical statement. And I like to emphasize at the beginning that when you take a partial derivative, if you don't keep this in mind, you will get in trouble. Especially the experimentalists got into trouble when they were doing this at first. You are working very hard to keep V and N constant. That's what it means to be a partial derivative. Seems like a small technical point, but it also works out to be an important point in conceptualizing what's going on as you start to change these things. Partial U, partial V. And you're going to fix S and N. So that's a fixed entropy process plus dN. And then we have partial U, partial N. And my objection as a student was this doesn't exist. But it will in what's called the thermodynamic limit. What do I mean that doesn't exist? Well, in our universe, particle numbers are discrete, correct? Particle numbers are discrete. They one at a time. You look like a continuous object full of water, full of salt, full of all kinds of nitrogen. If we break you down, you're nitrogen, a little bit of trace materials, hydrogen, oxygen, nitrogen, carbon. That's what we mostly are. And if I were to take you and count, hold your breath, cover your ears, I would get a number of particles for you. That number of particles would be on the order of 10 to the power 24, 10 to the power 25. So it is true that yes, you can only do one particle at a time. So a derivative in the sense of one particle at a time really doesn't exist mathematically, but we're not mathematicians. We're physicists and engineers. You're even further removed than us from worried about these technical points of it, right? You're just worried about getting an answer. That's what you're worried about. You're worried about getting an answer, a practical thing, right? So we're going to go ahead and work in the limit, that thermodynamic limit, where n is so big that it's just like if you were to take tangential example. You've written some code for calculating anything yet?
Yeah.
Okay. When you're trying to solve a differential equation, okay, we know how to do this. This is y of x is equal to a cosine alpha x plus b sine alpha y. No problem there, right? No, sine alpha x, sorry. Second order differential equation with constant coefficients. That's the most important differential equation in all of physics, probably. It happens for vibrational analysis and engineering and everything else. When you put this in a computer and try to solve it, there's no such thing as dx, right? You have to sit there because you can't have a continuum represented in a computer. You have to what's called discretize the line, and then you can solve it numerically, right? And it turns out you could, for example, that is really y of x plus delta x minus 2y evaluated at x plus y evaluated x minus delta x plus y, and this is all over delta x squared. Yeah, delta x squared plus y of x alpha squared equals 0. So you give it the first value, you give it the second value. So you give it this one, and you give it the one before it, and then it computes that one. And then what do? Then you put this one in here, and in here, and the next one, and the next one, and the next one, and the next one. So even though we certainly know that particle number is discrete, you can get a really good solution like that. In fact, you can get a perfect solution, almost perfect solution like that. How do you do this? Wait a minute. I don't know this of this well. Cut. Ah, look at that, I did it. So we define then, let's do it like I have it in the notes. This equation 4, 5, and 6. Every once in a while, I like to tell you where I'm at so you guys could see where I'm at. So this is equations 4, 5, and 6. Let's define T as partial U, partial S at fixed V and N. P as minus partial U, partial V. We'll see why that minus is there a little bit at fixed S and N. And then mu, which is called the chemical potential. Did you guys the chemical potential and what you did?
Yeah.
Okay. Partial U, partial N at fixed S and V. You'll see me write in the notes. Obviously, you know what these are because you've had 100 years of people writing textbooks about them. You know this is temperature. You know this is pressure. And you know this is chemical potential, although we didn't learn that in high school. I think Nigerian schools are so far ahead of us, you probably did. But chemical potential, Nigerian students, I shouldn't say this while I'm recording. I don't want to lose my job. Establishing that that's the temperature, partial U, partial S, that's the pressure minus partial U, partial V, and that's the chemical potential. That is what physicists do. There's nothing, if I were to write this down in front of students who have never heard of any physics, they could not disagree with anything up to here. They couldn't right now disagree with anything up to there. You know why? Because there's no physics in those statements yet. This is a statement about physics right here. The interpretation of partial U, partial S is the temperature, P is partial U, partial V negative, and mu is partial. That took work. That took work. And the analogy I always like to use is I've taught general relativity. I told you earlier I taught general relativity. There's a godzillion number of tensors you can write down. You have the E and M tensor in Jackson. You've seen it before, right? I don't think you've seen the E and M electron. There's a god. Look, I'll go back to E and M. Okay, there's a godzillion number of tensors with two indices you could write. Only one of them describes electricity and magnetism. Only one of them. Well, two is the dual tensor, right? Partial F mu, partial mu is X J mu. There's only two of them. Of all the godzillion number of things you could write down, all of the godzillion tensor equations you could formulate, somebody somewhere, that's a math problem. A physics thing is to say there's these tensors out there. That's the one that contains Maxwell's equations right there. That's the one we need. Minkowski did that. That F mu nu tensor was 0, EX, EY, EZ, minus EX zeros. That's what he did. That's what he did. That's something. I don't know if you appreciate it now. Yeah. But writing all of electromagnetic phenomena in two tensor equations, that's something. Yeah, it's incredible. Same thing with general relativity, which is all these you can write down a lot of tensor equations, but only one of them describes planetary motion, right? Only one of them describes black holes, the right one. And Einstein did that. All right. Very good. Okay. I would like you to notice about this while we're here, let's introduce some. So I guess in summary, I know I'm over talking this and I apologize, but I get so enthusiastic about things I really appreciate that I over talk them. It's awesome that people were able to do this. It's awesome. You think about how they must have struggled to make life easier for us to actually sit there and go entropy. That's what we're talking. There's something out there called entropy. It turns out, I think it was Carnot, as an engineering person, you would know this better, the Carnot cycle, right? He kept going around and he said, there's this one thing in here. There's this one thing in here that when you go around doesn't, turns out, uh, if you do it adiabatically, if you do this perfectly irreversible expansion and perfectly reversible expand, this one thing doesn't change. And I don't know exactly what it is, but it goes like 1 over T. And of course, the entropy ds is dq over T, right? And he didn't quite get that. He didn't quite get that. But they came along later and figured it out. Carnot, by the way, is an engineer. Carnot is one of the very few times that an engineer trying to solve a physical problem for steam engines made a fundamental contribution to physics, the Carnot cycle. The Carnot cycle, the best you can do, right? The Carnot cycle for reversible Carnot engine, the best you can do. I don't know that they knew that at that point. I don't know that they knew the Carnot. Of course, they couldn't. They didn't have enough. They didn't have enough of what we have now. But that's Carnot took a very concrete problem of steam engines and said, let's analyze this. And then that was one of the beautiful things he did was to idealize everything. I'm sure you've heard the phrase, consider the cow as a spherical milk source. You know, take a cow and just turn it into a sphere because that's all we can solve. Most of our in the life, as opposed to the engineers that have to get an answer for practical systems, physicists are so lazy. We just turn everything into a sphere, a box, or a cylinder, and hope for the best. We're just too lazy to work hard. All right. So again, it's each of these is a very interesting thing. If you look here, this is I'm going to write this now as du is equal to ds times t. And I had a debate. I'm going to do it this way. TDS plus PDV plus mu dn. What I would like you to notice about this is that you have something here that's intensive and extensive. Now, what does that mean? And I'm going here, intensive, P, extensive. And I'll tell you what these words mean in a minute. And I won't label it, but this is also intensive. Intensive means if I take the system, here's a box at temperature T, and I put another identical box next to them at temperature T, and I take this wall out, the temperature is T. It doesn't change. No matter how many of these, if I just keep making clones, doesn't change. Yep, they stay the same. However, entropy makes something, we just said it's, if you double the size of the system, you get double the entropy. There's more particles in it. Okay. Same thing here. If I take a box and it's got a pressure in it due to the particle motions all around, and I take an identical box with the particle motions all around, take the wall down, pressure is the same. Pressure hasn't changed. What has changed? Volume's twice as big. All right, volume's twice as big. So you have something that stays the same when you clone it. Clone. Well, clones are. It's the exact same thing. Just checking. Clone the system. One thing stays the same. Chemical potential stays the same. But the particle numbers, if you clone the system, double. If you double the size of the system. All right. And you can see here, these things generally, you see me say in the notes, some of these are easier to get than others, right? Some of these things are easier to get. It's pretty easy to get T, P, and V. It's not so much. So the problem with this formulation problem, T, P, and V are easy to get. I shouldn't say to get, easy to measure and control. All right. However, what's not so easy is S, mu, and N. So, uh, so maybe this is theoretically fantastic. Theoretically, it's utterly fantastic. In practice, though, if you want to talk to experimentalists, it's not that easy. Okay. So in class exercise, you see that I have all these things littered throughout here. So in class exercise, and I think I'm actually going to leave it for you guys at a later time. Define it. So we're going to define a new state function. It's called the free energy by F is equal to U minus TS. And we take the total differentials. Okay. So now this is what's called, and I don't know how much we do this in math methods. I don't know if we do this very much in math methods. I had a time says I can't always do every single point. But you had Goldstein, right? Do you remember how you did these canonical transformations? Yeah, I know you don't have context for this, but you had canonical transformations. Yeah, you have a coordinates that you had, these things of canonical's a different word for classical mechanics than the way we use it in this class.
Does
But
it have to do with Maxwell relation?
it had to do with equations of motion.
Okay.
Hamilton's equations, Lagrange. You make a canonical transformation from one set of coordinates to another, and you say that partial H, partial P, partial H, partial Q, and then partial K, partial capital Q. Well, that's actually a broader class of things called Legendre transformations, and that's what this is. So when you go from one type of thermodynamic state function, we start with U, the state function U and S. And if I take differentials here, df, I'll have du minus t ds minus s dt, because I'm taking the total differential. That's just the product rule from calculus, correct? So df then, we already know what du is. We just saw it from above, right up there. Okay. That is TDS plus PdV plus mu dn. And I'm going to ignore the mu dn for now. I just wrote it down to let you know. So I'm going to ignore the mu dn. We can leave it. Minus TDS minus SDT. So this is really just an exercise in calculus. In fact, it's calculus 2. Total differential. Oh, I need a haircut. I haven't seen myself on film in a long time. I need a haircut. No wonder my wife's complaining the whole. So watch what happens when we do this. This cancels. So I no longer have a differential. And now I see that df must be minus partial, and I'll define it this way, partial f, partial v. You can, the plus or minus is physics, not math. So partial f, partial v, dv plus, and this is a statement about, again, math. Partial f, partial mu, dn, minus, because I have a minus right here, minus partial f, partial t, dt. And this is at fixed. This first one's at fixed v. Oh, this one's at fixed. No, I did that wrong. It's partial f, partial t. Yeah, I got it right. dt. This one's at fixed v. This one's at fixed v and t. Fixed v and mu. And this one's at fixed mu and t. And that's just math. Identifying the partial without front is exactly why that statement, the identification of this with this, that partial f, partial v with p, and that partial F partial T with the entropy, that is exactly why I spent the time to write this down at the very beginning and make that connection with the partial derivatives. That's exactly why I did it. Most of my students, undergraduate students, have never thought of that before, as seen the correlation between a single letter up front, a single letter right here, a single letter up here, and the expansion of a total differential being a partial derivative. You guys probably have. You're a little older, a little more seasoned. Not as old in chronological age, but old in your career path, a little more experienced. So we see that we have in with the free energy, which is why chemists find this so important. We can calculate the entropy if we know the free energy at fixed V and mu. I don't have mu in the notes, but I put it up here just to show you I could do it if I wanted to. Partial F partial V at fixed T and mu. All right. So we will be using this F in general. I only have a T of V, but this is F of TV of N. And this now is a much more accessible thing for people in the lab to use. And if we can get this, it'd be great. It would be great. We're going to be, and I'm going to tell you something. I used to say this kind of as a joke. I don't say it as a joke anymore, especially with you guys, not so much. But for undergraduate students, I would tell them, I would make these statements. And I would tell them, you know what you need to do if you're having trouble with this? Write it down on this card. I used to say 3x5 card. But now this 4x6. These are bigger. These are bigger. Write it down, put a piece of tape in the back, stick it on your refrigerator door so that every time you go in there, you remember this important idea, this important equation, this important concept. Nobody ever does it. Nobody ever does it. I'm trying to think of a good example of it, but I can't off the top of my head. One will come to me. All right. So these two state functions are this one and U. So U, S, V, and N, and F, free energy, T, V, and N, related by a Legendre transformation, LT, Legendre transformation, are going to be used throughout this course again and again and again. So there you go. I give you the equations on actually, I didn't tell you this. Let me just pause real quick. All right, so let's talk about physics. That's kind of a mathematical prelude, but let's do some physics. So I'm at the bottom of page 2, but I'll actually be flipping over to page 3. And when you're reading from the computer, I like to tell you where I'm at so you can be there. So the laws of thermodynamics are, well, thank you for your patience in that discussion. I appreciate it, fellas. So let's talk about the laws of thermodynamics. We only have a few minutes left because I ran at the mouth. The laws of thermodynamics are statistical. What they really depend upon, is what's called the large N limit. So you'll see at the bottom here, the laws of thermodynamics, I italicize the word statistical statements about processes in the large N limit. So this should describe temperature, work, volume, pressure, all the thermodynamic quantities should be, if we do this correctly, we should be able, with very general principles, the laws of thermodynamics, we should be, with these very general principles, be able to lay a foundation that will allow us to describe macroscopic systems. But we are definitely going to be talking about N goes to infinity. And just a quick thing that has always struck me. If you were to take marbles and put them in a box about this big and shook them, 3 marbles, box this big, and I shook it. And I look in there and I ask you, what's the probability to find all the marbles in the right-hand side of the box? You got 3 marbles? Probability is pretty good. Not 0, not high, but you shake long enough, you can get 3 marbles all to land on one side of the box. Just look in there. Oh yeah, they're all down this type of. Most of the time they're whizzing around like this. You got 1 over here, you got 2 over here, 1, 2, 2, 1. Every once in a while you get 3. You get that. If I have 100 marbles in a box this big and I shake, the probability of finding 100 marbles in one end of the box is nothing. It just doesn't happen, right? So you can only imagine for a mole worth of gas, which is 10 to the power 23 particles, that you're never going to find them at the other in one half of the box, which is look around you. This is the thermodynamic limit. We are dealing in this class almost exclusively. I think there's one small example I do later with equilibrium processes. We're not out of equilibrium. This is what we're talking about. Nice, calm thermodynamic systems in the large N limit. You guys who are doing heat and transport actually have to, at the more advanced levels, I think, do have to worry about non-equilibrium thermodynamic processes. But for us, we're physicists, and like I said earlier, we're pretty lazy. So we're just doing what we can and let the engineers come along and really do the hard work to build a refrigerator. Okay. So that's what we're going to be doing. There are, I like to have 0, 1, 2, 3. By the way, every time you find a typo in the notes, I will put 50 cents in a box and I'll buy you donuts when we get to enough money. So every typo is 50 cents. All right. So if you find a typo, it's 50 cents. So the zeroth law, which is the only one we can do today, the zeroth law says there exists a scalar quantity, because I reworked these notes just for you guys. Actually, just for him, and I didn't know you'd be here. A scalar quantity such that if two systems, and I'll call them A and B for lack of better letters, and B are placed in contact, placed in contact, they reach, after a suitable time, a common value called their temperature. We define that to be the temperature. You know, the thing about, and we'll stop here. The thing about these concepts, though, we know them, we understand them as human beings.